All right, so we're going to talk about molecular polarity in just a second, but I just wanted to make clear one or two things. And so, when we're talking about seesaw and T-shaped electron geometries, we said that the reason that we take our first group from the equatorial position is that it minimizes the number of electron, like lone pair repulsion, with bonding groups at that 90-degree angle. So we took an equatorial position to only have two of those, and then we have two interactions that are 128 degrees apart. And then the reason that we take our second electron group, or the reason we put our second lone pair also in the equatorial position, is that if you were to have taken an axial position, so let's say you took this position right here, we'd have, I'll put sulfur here, you'd have a lone pair here, and then a lone pair here, and then you'd have, a fluorine, and a fluorine. And what you'd have happen if you took an axial position, you'd have these two 90 degrees apart. So you'd have these large lone pairs in very close proximity. And that's very unfavorable due to energetics. So it's not a stable state. But if you take the equatorial position again, and so we switch out, this for this, when we take that equatorial position again, we still have that lone pair that's 90 degrees separated from the two axial positions, but the separation between both of our sets of lone pairs is now 120 degrees. So we've separated those as much as possible. And that's the same reason that we do our specific removal of our octahedral to square planar and square pyramidal. When we remove our first electron group and switch it out for a lone pair, we can choose any position because all six of them are equivalent. But when we choose our second position, we want to separate those lone pairs as much as possible. So we choose the one that's 180 degrees apart from your previous removal. So you place them above and below the plane of the molecule. If we were to have taken one of them that's in that plane of the square, we'd once again have two of our lone pairs that are going to be 90 degrees apart from each other, using the example that we have here. And we just want to minimize having these lone pairs as close together as possible. We want to have them as far apart as we can. Okay? And so what we're going to talk about now is something about polarity. And so in the past, we had talked about the polarity of bonds, where we said that in bonds where you have a difference in electronegativity that is greater than 0.4, we have an unequal sharing of electrons in what we call the dipole. And we said that this unequal sharing is like a partial transfer of the electron. And so the atoms that are part of that bond get a partial charge, where the less electronegative atom kind of loses an electron and it gets a partial positive charge. And the more electronegative atom, like fluorine, it gains the electron. And so we notated that with that delta notation, where this delta plus means slightly positive, and this delta minus means slightly negative, because each of them has either gained or lost a little bit of electron density. And so where we can have the polarity of a bond at a time, we can also have polarity of whole molecules. And so what we're looking at here is just the same molecule, HCl, and I'm showing that electron density map that shows, in blue is low electron density, and in yellow, red is high electron density. And so we can look at the molecular polarity, which is just going to be the sum of your bond polarities. And so we'll start by looking at diatomic molecules. Meaning, in this case, they don't have to be the same molecule. The same two atoms. So something like HCl is technically a diatomic molecule. And so we'll say that diatomics with polar bonds are themselves polar. And that's because polarity comes down to that single bond. So polarity of molecule needs a C in there, comes down to that one bond. So something like HCl is polar because it has that polar bond. If you have a diatomic that has nonpolar bonds, so diatomics with nonpolar bonds are themselves nonpolar because the bond that joins them together, because it's nonpolar, you have equal sharing of electrons, you don't have any difference in the polarity. And so when you have something like oxygen double bound to itself, this is also a diatomic. The difference in electronegativity here is 0, and so we would say this is a nonpolar bond. So nonpolar bond, and that nonpolar bond gives us a nonpolar molecule. And so this is kind of, a little bit boring, and it gets a little bit more exciting when we look at polyatomic molecules. And so the first example is we're going to look at polyatomic molecules that are linear. So those that have 2 electron groups around them. And we'll say that when we're looking at the sum of bond polarities, we'll calculate something called the net dipole moment. And that's just our fancy way of saying the sum of bond dipoles. And so we're going to see 2 different cases. In the one case, if the dipoles point opposite directions, they cancel out. And so if we look at something like CO2, electronegativity of oxygen is 3.5, carbon is 2.5, oxygen is 3.5. We can draw the dipole, having our arrow pointing towards the more electronegative atom, and we put the plus on the positively charged, or the thing that's going to end up with a partial positive charge, and we see that these 2 arrows point in opposite directions. And so what we're going to see in the next slide is that the way that we look at this is we do something called vector addition, which I'll kind of show on in a little bit, and that just means that we take one arrow and we put the head of that, or we can basically match them up like this. We add them together, and that equals 0 because they're in equal and opposite directions. If you have a case where the arrows point in the same direction, you get a net dipole. Okay, let me drag this here. That's good enough. And so, oh, come on, work with me here. Okay. And so we can say if dipoles not equal and opposite, you get a net dipole. And so we have the example of hydrogen cyanide here, where if we draw in and put in our electronegativities, hydrogen is 2.1, carbon is 2.5, and nitrogen is 3.0. We have that, the carbon-hydrogen bond is technically not nonpolar. And so we don't really have to show that one. So we actually only have one polar bond here. But if we were to have drawn in the dipole for the carbon-hydrogen bond, it would point towards carbon. And so in this case, you have a net dipole, kind of just focusing on the actual polar bond where we only have one arrow. We have a net dipole that points towards the nitrogen. So net dipole, in this case, we're not really summing, but we see that we have one nonpolar bond and one polar bond. Your net dipole points this way. And so this gives you a polar molecule. Whereas before, when we had them canceling out with CO2, this gives us I'm going to write this in blue. This gives us a nonpolar molecule. And so let's look at things that are a little bit more exciting than simply just linear. Let's look at things that have a tetrahedral electron geometry and differing molecular geometries. So if we look at something that is bent, like water, we know that the electronegativity of everything here, 2.1 for each of your hydrogens, 3.5 for the oxygen. We can draw those dipoles from hydrogen to oxygen, pointing towards oxygen. And we're going to take those and we'll add them together. So we'll add dipoles together, tail to tip. Or we can say tip to tail or tail to tip. Tip to tail. So I'm going to draw my first one that points up like this. And so that was, this one. Now I'm going to draw my second one, and I'm going to put the base of it at the head of the former one and draw it up. And so that's what, in blue here is this. And so I'm going to draw the net dipole as taking an arrow from the base of my first arrow and point it to the head of my final arrow. And so if I draw that, I get that the net dipole points like this. And so I'd say that my net dipole looks like this. And so we can also draw it here, where it goes basically from the midpoint of the two hydrogens and point up towards the oxygen, because the left to right nature cancels out, but the up nature adds together here. And then we have something like ammonia, which is trigonal pyramidal. We can write in each of their electronegativities. Hydrogen is 2.1, nitrogen is 3.0. We can draw in the bond dipoles like this. And in this case, it gets a little bit harder to do, but for what it's worth, the net dipole here is also pointing basically from the base of the molecule up to the nitrogen. And that's because the 3D aspects of the two hydrogens kind of cancel out, like going behind the board and, coming out of the board and going into the board. Those two dipole, the 3D, like the Z coordinate cancels out, and you really only get like a Y coordinate that goes up. So in this case, we can just say 3D component cancels out, just like it kind of canceled out for the left to right nature of oxygen. And so we have this aside of vector addition. When you have something that's 1D, the way that that's added is tip to tail. And I have this as part of the post-it slide. So if you have, a vector like this and a vector like this, their sum is just going to be a longer vector like this. If you have a vector like this and a vector like this, their sum is going to just be, they add together to give you nothing. That gives you nothing. And then if you have a large vector like this and a small vector like this, the sum here is just a slightly shorter arrow. And you can think of that by just basically taking, if we take this right here and then bring it up to above, that turns into this. And then if you take this one, you're just putting a small arrow right here. Okay. And then in 2D space, if you have something that points like this and something that points like this, the sum is, as we did with water, it looks like this. And so you get, a net up here. And if you have the case where you have something that goes like this, something that goes like this, the sum here is that you have and then ba, and then it goes like this. And then finally, we have 3D space, and this gets a little bit harder, but I'll draw it here. And so you have, in the case of NH3, we had an arrow that went like this. And really, I guess it might make more sense to draw it like kind of wedged, so a little bit thicker. So you had one arrow that points like this. You had one arrow that was kind of dashed because it was going into the board, so it's like this. And then you had one arrow that was like this. And in this case, like I said before, the 3D component kind of canceled out here. And you just want to make your best guess here. And so the net dipole here was, that which was thick kind of coming out. That which was thin kind of going, back into the board. And then that one that was just like pointing normally is just like this. And so like the net was just a straight up and down. And so I have posted in the posted slides like maybe a little bit better representation of each of these, just showing what that vector addition looks like. So like I said, for 1D, effectively what we're doing is this and this together gives us a long arrow like this. And then in the case where we had nothing, we just, we kind of stack them on top of each other to do something that looks like this. So we had an arrow this way, had it with an arrow this way, and that's what gave us nothing. And then with our last one, where we said like one long, one short, you take the long one, you take your short y, and then your sum is just, what you get from adding those two together. So it's this thing right here. Okay. And so when we're looking at molecules, I want you to take a chance or take a stab at this. And, we gave the example of, water and NH3. Now I want you to take the next minute or two to pause the video and then tell me what you think the polarity of each of these molecules is. And so if it's pertinent to you, I'm going to write in those electronegativities. Chlorine is 3.1. Selenium is 2.4. Fluorine is 4.0. Sulfur is going to be 2.5. Sulfur 2.5. Fluorine 4.0. Chlorine, as before, 3.0. And then for krypton, it's just lower. We typically don't report the electronegativity for those noble gases. So pause the video here and then come back, and then we'll talk about the electronegativities here. Or we'll talk about polarities. All right, welcome back. And so the first thing what we want to do here is we're just going to draw the dipoles for each of our different bonds. So we have the dipole for selenium. It goes from selenium, points towards chlorine. And so when we look at this, what we see is that actually our axial positions will cancel out. So the arrow pointing this way and then the arrow pointing this way, so which I'll highlight in yellow, these two just cancel out with each other. So the two axial positions cancel out. So we can just say this is like 0. And then we have that from each of our chlorines. So one's pointing up, coming at us, and then one's pointing like away. But we can just kind of add them like they're 2D. And that would give us that the bond dipole is generally in this direction. So we'd say that because this is asymmetric, you'll find that most asymmetric molecules are going to be polar. So we'll say asymmetric, so this is polar. We can then look at sulfur hexafluoride. Once again, our dipoles point from sulfur towards fluorine. And we can draw all of these in. But in this case, we have a symmetric molecule, and the two axial positions are going to cancel with each other. And then each of the positions that basically are 180 degrees are going to cancel as well. So this fluorine is going to cancel with this fluorine. And then finally, I'll do this in pale pink. This fluorine cancels with this fluorine. So because these things are 180 degrees apart, they're equal and opposite. So we would say that this one is net nonpolar. And that's just because each bond dipole has equal and opposite partner 180 degrees from it. Okay, so that's nonpolar here. This one's polar. We can look at krypton tetrachloride. We draw in those dipoles here. And then similar to that last question, we have these chlorines are 180 degrees apart from each other. These chlorines are 180 degrees apart from each other. This is a square planar geometry. So this is square planar. And all of the dipoles are symmetric. So we'd say this is symmetric. And this one ends up being non-polar. And then we can also write in what the geometries of each of these were. This one's seesaw. So you'll often see seesaws are going to be polar. And this one's octahedral. Our final one is this SF2. And so this one kind of looks like water. And we're going to have our dipoles point this way. And the way it's written kind of makes you think that these dipoles might cancel out. But we want to remember that this is actually something that looks bent. So we have sulfur, fluorine, fluorine, lone pairs up here. So when we draw in those dipoles, we actually see that they add together. So we can, draw each of those vectors, add them together. We see that our net dipole points down, and then that would give us if we have a net dipole, we get a polar molecule. Okay? And so the last question I have for you that relates to this polarity is this one right here. And so what I'm asking you to do is draw the following compounds out, draw them with correct electron geometry, and then determine the molecular polarity. So pause the video here, draw each of these out, and then we'll come back and draw these up. All right. So welcome back. I'm gonna go a little bit fast through this, so pause if you need it, but I'm also gonna be explicit. So if you need to, you can go ahead and jump ahead if that is applicable to you. So I'm first gonna start by counting up each of my electrons. So from hydrogen, I get 1, and I have 2 of those, so I have 2 electrons from hydrogen. From carbon, I have 4 times 1, so that's 4. And from oxygen, I have 6 times 1, so that's 6. So this sums to 12 total electrons. I'm gonna draw that up. I have carbon, I have oxygen, I have hydrogen, and I have hydrogen. So I'm gonna form single bonds here, and I'll be explicit for this one, and then for the other 3, I'm just gonna draw out the structure. So I'm gonna form single bonds between all of my atoms. So I'm gonna spend 6 electrons on single bonds. So I'll say bonds here. And that leaves me with 12 minus 6, 6 electrons left. The next thing I'll do is I'll put lone pairs around that oxygen to give it an octet. So I have 6 electrons on oxygen lone pairs. So lone pairs. That actually leaves me with 0 electrons. But if I look, I can see that my carbon only has 6 total electrons, whereas everything else, oxygen has 8 electrons, and each of the hydrogens, I'll do in pink, each of these have 2 electrons. And so in order to get my carbon, which I'll actually circle in a different color to make it a little bit easier, we'll do that in gold, maybe. This only has 6 electrons. In order to get my carbon up to those 8 total electrons, what I'm going to do is I'm going to use 2 electrons from oxygen to make a double bond. And so if I make that double bond, I'll go like this, I go like this. My net structure is going to be something like this. Carbon, double bound to oxygen, hydrogen, hydrogen. Now I can draw in my dipoles. Hydrogen is 2.1, carbon is 2.5, 2.1, 3.5. So the carbon-hydrogen bond is actually nonpolar. So our only polar bond is going to be between carbon and oxygen. That points like this. So we'd say that this is a polar molecule. And if we're assigning what its electron geometry is, we say this is tetrahedral. Okay, we can come to CH3OH, which, like I said, I'm just going to draw it now. That molecule looks like this, CHHHOH, with oxygen having 2 lone pairs on it. And so if we just draw this one up, in this kind of linear form, it would suggest to us that when we draw in our dipoles, carbon, as before, hydrogen is 2.5, carbon 2.5, hydrogen 2.1, carbon 2.5, oxygen 3.5. We see carbon points towards oxygen, hydrogen points towards oxygen. This looks like maybe these should cancel out. And, keeping in mind that the actual difference in electronegativity is different between those two, but it's important to draw this one out in that 3D form. And so when we draw this in 3D form, we have carbon, which is tetrahedral. So we're going to draw hydrogen. Oh, that was bad. So we're going to draw in each of the groups that surround that carbon. So we have a hydrogen, we have a hydrogen, we have a hydrogen, we have an oxygen. And then if we treat the oxygen as our new central atom, we know oxygen has 2 electron groups around it that are bonding, and then 2 that are lone pairs. And so we'd say that the carbon, while it's tetrahedral, the oxygen is bent. And so when we draw oxygen in that bent conformation, what we'll see is that in this case, we actually have a a case where those dipoles are going to add together a little bit. So we can add those two dipoles together. So we have one that goes up like this, one that kind of like goes down like this. And so the net dipole, we might say, looks a little something like this, where we point like this, effectively pointing towards the oxygen. So we'd say this is a polar molecule, and the geometry you'd have to define based off of which atom you're looking at. If we look at ClO, this is a diatomic, so we just have to see if we have an actual difference in electronegativity here. So you have ClO, and everything gets a lone pair here, keeping in mind that we have that negative charge. So that helps us get to the correct number of electrons. If we look it up, chlorine has a electronegativity of 3.0, oxygen has one of 3.5. So we point towards our more electronegative atom, and we'd have a polar molecule here because we only have one type of bond. And we'd also say this is linear. And then finally, we have NH4+. And so when we draw that up, we have 8 total electrons, and we spend all 8 of those electrons forming bonds between the nitrogens and the hydrogens. So this is a positive thing. And if we draw in each of our electronegativities, hydrogen is 2.5, nitrogen is 3.0. We could take our red here, we'll draw each of our polar bonds, and they all point towards nitrogen. And in this case, as is the case with many molecules, if you have a symmetry across the whole molecule, all dipoles are going to end up canceling. And what that means is that this is a net non-polar molecule. And if we wanted to write down what its geometry is, we'd say this is tetrahedral. Okay? And so the whole reason that we're looking at doing all of this polarity is that the polarity of the molecules determines the property of the compound. And so when we talked about, things being soluble, insoluble, etc., reminding ourselves that solubility means ability to mix, things being, in some cases, what determines the solubility of something is the polarity of the molecule. Because we know that something like water is very polar. And so you might have heard in the past, when we talk about solubility, like dissolves like. So things that are polar are really good at dissolving things that are polar. And things that are nonpolar are good at dissolving things that are nonpolar. And so when you take something like oil and water, the reason that they don't mix is because oil is nonpolar and water is polar. They're two different types of, molecules at that point. They don't get to have, good interactions with each other. Whereas like if you take a polar thing and have it interact with a polar thing, you can orient the negative parts of one polar molecule towards the positive parts of the other. So polar molecules can match up oppositely charged regions. And we'll get into this in Chem 1b and 1c. We'll talk about something called intermolecular forces, opposite charged regions. And these intermolecular forces are really due to the polarity of a molecule. And we'll talk about how nonpolar molecules, they have a specific type of interaction that is kind of favored by having another nonpolar partner. And so in addition to solubility, polarity is also going to determine things like boiling and melting points. Once again, this kind of comes down to those intermolecular properties or intermolecular forces, where things that have strong intermolecular forces tend to have higher boiling and melting. Well, higher boiling and lower melting points. So depends upon forces and polarity between molecules. But like I said, we'll get into that a little bit more in 1G. Okay? But that's where we'll end our discussion of chapter 10. And what we'll do is we'll start talking about chapter 11 in our next lecture.